So here's an overview of the remainder of today's lecture. We're going to describe the basic framework of global linear models, and we'll see that they offer a very different way of thinking about these supervised learning problems from the history-based models that I just discussed. We'll talk about parsing problems in this framework, in particular re-ranking approaches. And finally, we'll talk about a variant of the perceptron algorithm, which can be used for parameter estimation in these global linear models. So one key idea is the following. We'll move away from this idea of derivations, or in particular, we'll move away from this idea of attaching probabilities to individual decisions which go into building an entire structure. Instead, we're going to talk about feature vectors over entire structures. We'll call these global features. And this is really where the name global linear models comes from. So now we're going to define functions which, for example, look at an entire parse tree and map this to some feature vector. So in one sense, these feature vector mappings will be very closely related to the feature vector mappings we saw for log linear models. But in another sense, there's a rather more radical move here to a situation where entire structures are getting mapped to these feature vectors. There are several reasons for thinking about these models in these terms, or there are several reasons for introducing global features. First piece of motivation is that it can offer considerable freedom in defining features. So this will allow us to incorporate all kinds of features and all kinds of information within our supervised learning problems, which were really challenging to include in the history-based models that we've seen up to this point in the course. So let me give a couple of examples of features in the parsing problem, which, as we'll see, are quite easily incorporated within a global linear model, but which are much more difficult to incorporate within, for example, a probabilistic context-free grammar. So this is one observation by Mark Johnson and some others from 1999, which is that there's a definite tendency in natural languages for something called parallelism in coordination. And this is essentially the following. So if I look at these two phrases, I have bars in New York and pubs in London. The second phrase, I have bars in New York and pubs. This one has an instance of parallelism. And that's because bars in New York has a very similar structure, syntactically speaking, to pubs in London. So I have two things being coordinated here which have basically similar structures. If we look at the second example, this does not have parallelism. So we're coordinating bars in New York with pubs, and these two constituents do not have the same internal syntactic structure. So statistically speaking, we seem to see a preference for these kind of structures as opposed to these. And this kind of preference can come in useful when we're trying to disambiguate structures. So if I say, for example, I visited bars in New York and pubs in London, there are going to be a few pauses here, and some of them are going to include this sort of parallel structure where these two things are noun phrases and they're coordinated. And some of these structures will not include these two parallel structures being coordinated. Knowing that there's a preference for parallelism and coordination can help me give a preference for parse trees with these kind of parallel structures. Now, I would challenge you to go back to the lectures on probabilistic context-free grammars and try to figure out how to incorporate this preference within a probabilistic context-free grammar, because it is really not entirely straightforward. So that will be one of the motivations for global linear models. We'll see that it's actually very easy to incorporate this kind of feature within that model. Here's a second example of the kind of features which might be useful, but which are again rather difficult to incorporate within a history-based model, such as a probabilistic context-free grammar. These are semantic features. So imagine we have an ontology or some kind of lexicon which gives properties of different nouns and verbs. So one example of such an ontology might be a resource called WordNet, which is a very famous resource that has an information about a very large category of nouns and verbs in English. And this ontology might state, for example, that the word cappuccino has the plus liquid feature, whereas the word book does not have that feature. Okay, so cappuccino is a liquid. And that's important if we're thinking about a verb like pour, where in general nouns which have a plus liquid feature are likely to appear as objects, whereas nouns which are not liquids are much less likely to be objects. So this kind of ontological information, where different nouns have different properties, can be quite useful again in modeling the probability of different parse structures or in disambiguating different parse structures. So say we'd like to build a parser that has a preference for the verb pour taking nouns with the plus liquid feature. Again, I would challenge you to think about how we would incorporate these kind of features within a probabilistic context-free grammar. It is somewhat challenging. Whereas again, we'll see with global linear models, it's relatively easy to incorporate these kind of features.